So today we're going to be having a look at dilations and reflections of quadratic functions. Before we do that, I want to ignore the word quadratic and I just want to talk about functions. We're going to be working through transformations for a fair bit, and we're also going to be working through functions. We are going to learn about a lot of different types of functions. And so it does us no good to learn about transformations in a vacuum, specific to exactly one type of shape, a quadratic. Earlier, I did a parallelogram and I did a triangle, right? Two different shapes. If you can reflect one, you can reflect the other. It doesn't matter what shape it is. The issue often comes down is that we become quite good at transforming quadratics, but we become less successful at transforming other functions. So I'm going to teach you the dilations, horizontal and vertical, and the reflections using function notation. So let's start off with our dilations. So for a horizontal dilation, by a factor of x, let's call it x, let's call it a, f of x, the function, becomes f of x on a. Okay? So as an example, if I had the function x squared, well, x squared would become x on a squared, which is x squared on a squared. Okay, so you can see that when I put something inside the brackets with the function, it affects only the x. And because of order of operations, the squared happens afterwards. It does not become x on a squared. It specifically becomes x on a in brackets squared. So just be mindful of that. Okay, so that's horizontal dilation of a factor by a factor of a. Let's do vertical dilation by a factor of b. Alrighty. So for a vertical dilation, f of x becomes b times f of x. Okay? So if our function was 3x minus 2x squared, then it would become 3x minus 2x squared multiplied by b. Okay? So it multiplies the entire function. Meaning, after you expand the brackets, you would get 3bx minus 2bx squared. Notice it's different than when we do a horizontal dilation. The horizontal dilation goes inside the brackets of the function notation, whereas for the vertical dilation, it goes inside on the entire function. Let's have a look at reflections. So for a horizontal, an x-axis reflection, we learned last time, we thought about it in terms of x comma y becomes x comma negative y. Well, using function notation, we can write this as x f of x, so it becomes x negative f of x, meaning for an x reflection, you take f of x and you make it negative. For an example, if you have 3x minus 2 and you want to reflect it, you just get minus 3x minus 2. The whole thing should become negative 3x plus 2. If you want to try any of these reflections, you're more than welcome to chuck onto Desmos these different ones and see how they work. And for the y-axis reflection, right, from our work last lesson, we saw that x comma y becomes negative x comma y. Change that y to an f of x because we're using function notation. And now we can see that f of x, the x is the thing that changes, so it becomes f of negative x. So in the case that we get something like x squared minus 3x is going to become minus x squared minus 3 minus x. Minus x squared is just x squared. Minus 3 negative x becomes minus minus, so it's plus 3x. Okay? So that's how you perform a horizontal dilation by a factor of a vertical dilation by a factor of b, an x-axis reflection, or a y-axis reflection using function notation. I'm just going to put them all on one just so you can see them nice and easily. Alrighty, so this is the shorthand version. In this case, I've just swapped a and b for the vertical and the horizontal dilation. It doesn't matter, they're just arbitrary constants. So this is a horizontal dilation by a factor of b, and this is a vertical dilation by a factor of a. Alrighty, so that's to give ourselves a little bit of assistance. Now let's talk about quadratics and see when this happens. So, alrighty, so we've got the function f of x equals 3x minus 4x squared, and we're firstly going to dilate it vertically by a factor of 3, and then we're going to reflect it in the x-axis. So just as a reminder for the dilation, so this is for the first part, we're going to get f of x becomes 3 times f of x. And for the reflection in the x-axis, f of x is going to become negative f of x. Okay, so those are the transformations. I'm going to change this f of x to a g of x, just to avoid confusion. So, part A, to dilate it vertically by a factor of 3, g of x becomes 3 times g of x. Alrighty, so just imagine we multiplied both sides by 3. Where would the 3 go? 3 times the entire function, 3x minus 4x squared. Expanding brackets, we get that the new function would be 9x minus 12x squared. Remember, just from expanding brackets from before. Alrighty, so we now have a new function, 3 times g of x, which is 9x minus 12x squared, which has been dilated vertically by a factor of 3. Okay, so let's call this new function, well, after g becomes h, so let's call it h of x is equal to 9x minus 12x squared. Alrighty, and let's now do part b, which is a reflection. And remember, it's going to mean that h of x is going to become negative h of x. Alrighty, so let's do that. So h of x is equal to 9x minus 12x, and it's going to become minus h of x by the rule, which is equal to negative, in brackets, 9x minus 12x, and we get negative 9x plus 12x after expanding those brackets. Oh, I've lost the squared somewhere along the way. There it is. The squared came home after all. Alrighty, so that's a little bit on dilations and reflections. I might just go through one more example. If you're feeling confident, you can move on, but I'm going to show you how to do horizontal and y-axis reflections. So horizontal dilation by a factor of a half and reflect in the y-axis. Alrighty, so let's just remember ourselves what a horizontal dilation looks like. It's f of x becomes f of x on whatever the factor is, in this case a half, so it's x on a half. Now, you might need to have a think about this, but if I take x and I divide it by a half, there's a better way of writing this. Well, this is equal to x divided by a half, and if you remember your fraction rules, you'll know that you can change divide to times, and this is just really x over 1. X times 2 is 2x, 1 times 1 is 1, so it's 2x over 1, or just 2x. So this really becomes f of 2x. Okay, so it's like an inversion sort of thing happening there. Okay, so just a quick aside on how to divide by fractions in case you've forgotten. Remember that you can change the x on 1 divided by 1 on 2. Remember, you can always change it to multiplication if you flip the second fraction. All right. So back to what we're actually talking about today. So a y-axis reflection is f of x becomes f of negative x, okay? So those are our two rules that we're going to be using in order to actually do this. And now what we need to do is actually have a crack at doing both changes at once. So let's start with the first one. So for part A, if we've got q of x is equal to 3x minus 4 squared, well, after doing this transformation, we're going to get q of 2x. Okay? So wherever we see x, I'm just going to replace it with a 2x. So we're going to get 3, 2x minus 4 squared. Alrighty, and so that's our transformation done. But of course, q of 2x looks a bit funny, so let's just call it, well, after q, how about p? So we've got p of x is now equal to 3, 2x minus 4 squared. Okay? So let's go through and now reflect it in the y-axis. So we've got p of x is equal to 3, 2x minus 4 squared. And we can now do the transformation, which is make it p of negative x. So once again, when we see x, we're going to make it negative. So 3, 2, negative x. Remember, that's not minus, that's multiplication, because they are right next to each other. Minus 4 squared. 2 times negative x is just negative 2x minus 4 squared. Now, perfectly happy if you've got, I don't know, let's call this after p, q, r of x is equal to that. That's perfectly fine, nothing wrong with that. I'm going to show you just how to simplify this just a little bit further. Totally irrelevant to what we're learning today, but I think it's important that we can recognize when we can do a little bit more. First thing I'm going to do is I'm going to factorize out the negative 1 that they both have. So I'm going to factorize out this negative. So we get 2x minus 4 squared. Okay? Now, if you, plus, right? Because I've just taken that factor out, right? Because remember, expanding, I could just put it back in. But anyway, this is just a quick recap on factorization. But notice what we can do. What's a negative squared? Well, a negative squared is a positive. And so this is really just 3 of 2x plus 4 squared. The fact that both terms are negative means that both of the negatives can be factorized out and then squared, which gets rid of them. So that is just a slightly cleaner looking version of the previous one. Alrighty, I'll see you in the next one. Bye-bye.